Good morning everyone, I'm Stefano Marchesi. In this talk I will present the first results of the redshift identification of the X-ray selected active galactic nuclei in the J1030 field. This talk is a summary of the results that have been published in this recent paper that has been published on ANA last year. So to start, let's take a look at the Chandra J1030 field. So this is a field that has been targeted by many different facilities over the past 10 years. And recently it has also been the focus of a deep Chandra observation, a 0.5 megasecond observation that was taken in between 2017 and 2018. The results have been published in Nami et al. 2020. 256 sources have been detected in this observation of a pointing of about 0.15 square degrees, and this makes J1030 the fifth deepest X-ray field currently existing. As you can see here in the right panel, there's the flux on the y-axis and on the x-axis the area of many different X-ray surveys, and J1030 stays here at the very left and reaching fluxes that are comparable with those of some of the most famous deepest fields. Thanks to the excellent multiwavelength coverage of the field, we were able to find an optical or infrared counterpart for almost all the objects. And in particular, we found that 243 sources are extragalactic. Then there are 7 sources that are stars, and 6 of them don't have a counterpart. They may be spurious, or they may be objects that are too faint in the optical and near infrared. So the next step was finding a redshift for all these Chandra X-ray sources. So we started an extended campaign with many different spectroscopic facilities. In particular, there was an extended effort with INAF LBT, with mods, in particular with the multi-spectrograph mods, which allowed us for finding overall a spectroscopic redshift for about 50% of the population, and the fraction is even slightly larger if you take into account only the 243 extragalactic sources. The population is quite a mixed bag of sources, as it is expected for objects that are relatively faint in the optical and in the X-rays, like those in the J1030 deep field. And in particular, about 50% of sources have a spectrum that is dominated in the optical by the AGN emission. 43 objects are classified as broadline AGN, 20 of them are classified as narrow-line AGN, and then the remaining 50%, more or less, is host galaxy dominated. There are emission line galaxies and early type galaxies in this population. Now the point here is of course that even those sources that are galaxy dominated are AGN, we know it from the X-rays, but nonetheless these are objects where the optical emission is dominated by processes that are not directly related to the AGN. This is just a summary of the 4 classes of sources with a spectrum for each of them. This is a very clear broadline AGN, redshift 2.7. Then we have a narrow-line AGN at a much lower redshift, 0.39. And then in the bottom part of the slide, there are 2 spectra where the emission is dominated by non-AGN processes. On the left, there is an emission line galaxy, while on the right, there's an early type galaxy. Now, the problem with the spectroscopic redshifts is, of course, that they are more and more difficult to find once one moves towards fainter fluxes. And here there's a plot of the distribution in optical magnitude, more specifically the R-band magnitude of our sources, as a function of redshift for the 4 different classes of objects that I mentioned before. And as you can see, there's a steep decline in the number of sources detected moving towards fainter fluxes. And this, as a consequence, means that we don't have a lot of spectroscopic redshifts for sources moving towards high redshift. At high redshift, we are biased towards very luminous broad-line AGN for the most part, but we are not able to detect a lot of narrow-line AGN, and certainly we are not able to detect sources in which the AGN emission is not dominating the optical near-infrared SED. As a consequence, the spectroscopic population is skewed towards a fairly low redshift, an average redshift of 1.2, and the maximum redshift for which we got a spectroscopic redshift is 3.98. We are not including in this discourse the J1030 itself, which is a redshift 6.3 quasar on which the field is centered, because of course the field has been selected based on the presence of this extremely luminous QSO, and so of course it was not randomly found in the X-ray survey. So these are the spectra of the two sources that actually get J1030. By chance, there's one broad-line AGN and one narrow-line AGN. The third source, as I said, is the redshift 6.3 QSO J1030. But of course, this is a limitation because we expect to have much more sources among the 256 in the Chandra J1030 field. So to increase our knowledge of the overall population, we need to use photometric redshifts, in particular to sample the faint population, so those sources that are too faint to get a spectroscopic redshift. Photometric redshifts are a sort of low-resolution spectroscopy in a sense, meaning that we are using photometry at different wavelengths to get a measurement of the redshift of the source. And as I said, this is key to get a redshift for those sources that are too faint for spectroscopy. To get reliable photometric redshifts, one needs two things. One is a reliable set of synthetic spectra, spectral energy distributions, both for passive galaxies, where the emission is dominated by non-AGN processes, and of course of AGNs. And then the second thing is to get good photometric redshifts over a wide range of wavelengths, ideally starting from the near UV, the U bands, up to the far infrared. There are many different tools that that can be used to determine photometric redshift. In our work, we made the use of Hyper-Z by Bozzonella et al. 2000, and we also validated the results with another tool that is called EASY, that has been published a few years later. This is, in the bottom panel, is an example of an SED fitting for a source which is fairly faint, in the R band is around 24 or less, for which we determine a redshift of about 1. On the right panel, you see here is the probability distribution function of the redshift, which is associated to each source with a photometric redshift. So we don't have just a single value, but we also have a distribution of probabilities, and we can treat photo-Z's in a statistically significant way. To compute photometric redshifts, we take advantage of the extensive multi-wavelength coverage of the J1030 field. The field has been targeted in a variety of bands, in the optical up to the near-infrared, and more recently also in the millimeter band. This is a summary of the filters and of the different surveys that we used in our work to compute photometric redshifts. To assess the reliability of these photometric redshifts, one needs to do a comparison with the spectroscopic redshifts. In this plot here, I'm showing on the left the trend between photometric redshifts on the y-axis and spectroscopic redshifts on the x-axis for the different classes of spectroscopic redshifts that I've discussed a few minutes ago. And it can clearly be seen that the majority of outliers come from a particular population, which are broadline AGNs. Indeed, the SED of broadline AGNs is difficult to reliably constrain, especially once one lacks of narrow-line photometry, which is key to measure accurately the emission in narrow emission lines, which is typically observed in broadline AGNs. Given that we don't have a narrow line photometry in the J1030 field, the accuracy of the measurement is the lowest in broadline AGN. In the other classes, the agreement is much better, and as you can see in the right panel, for the population of sources that are where the optical emission is dominated by the host galaxy rather than by the AGN, the agreement between the photometric redshift and the spectroscopic one is excellent. And this is important because we don't expect to have a lot of broadline AGN in the population of sources that don't have a spectroscopic redshift, given that these sources are going to be fainter, and we expect most of the broadline AGN to be in the bright end of the population. Just to give you a reference, this is a summary of the reliability of the photometric redshifts in our work compared to those of different other surveys. And there's a very good agreement between our results and those obtained in other surveys which had a comparable number of photometric data points and lack of narrow band photometry. So this is just a reference. The spectroscopic and photometric information presented in the first part of the talk is available online. You can find the web page at the link reported here. And for each source, you can download the spectra in FITS format and SEDs and probability distribution function of the photometric redshifts in ASCII and FITS format. This is a page that is open to the public, and I hope that it is going to be used by the community extensively. For the second part of the talk, I want to highlight some first results that have been obtained using the Chandra J1030 catalog of redshifts. The first result makes use of the spectroscopic redshift sample. In these plots here, I'm showing the cumulative distribution function of AGNs with a spectroscopic redshift. This means that the values on the y-axis start to 0 for no source and end up eventually to 1 for all sources with a spectroscopic redshift. So this is an histogram normalized to see each source moving ahead. And you can see here that what we find is that AGN detected in the X-rays are excellent trackers of a large-scale population. This is something that has already been observed in previous X-ray surveys, and is due to the fact that the density of X-ray AGN in a field is very small. So even a small number of sources at the same redshift or in a very narrow redshift range track excellently the existence of structures. This is confirmed when one adds also sources that are not detected in the X-rays, as in the case in these plots. In black here you are seeing X-ray detected sources. In white you are seeing all sources for which we have a spectroscopic redshifts. In many cases, the presence of a structure in the X-rays, those flagged with an arrow in the 4 different plots, is confirmed with a much larger number of sources once you check for the overall population. And this is a visual example. On the left we have the Chandra field with all the different structures that we detected flagged in different colors. If we zoom in and we take a look at the structure at the lowest redshift, redshift 0.16, in solid we show the sources for which we have an X-ray detection. This is an optical image though. So there are those sources, precisely there's 4 of them, but there are many more that are not detected in the X-rays but are at the same redshift. So this proves that indeed these structures can be treated very well based on the X-ray information alone. And this is a summary of the different structures that we detect, the number of sources detected in the X-ray sample and in the overall sample, and the probability that such a number of sources can be detected by chance based on the background population. And you can see that in many cases, even with 3 or 4 sources, we track structures that are then confirmed at a much higher level of significance in the overall population. A second result that we obtained using the Chandra J1030 sample is a first characterization of the high-redshift population, and in particular we computed the redshift greater than 3 number counts. Now, as I mentioned earlier, there are nominally quite a lot of sources in Chandra J1030 at redshift greater than 3, particularly there are 25 of them, but only 3 of them have a spectroscopic redshift. All the others have only a photometric redshift. For this reason, we decided to use a probabilistic approach, and rather than using the nominal values of the photometric redshifts, we use the probability distribution functions. In this image, you see the spectral energy distribution of a high redshift object in the Chandra J1030 sample, a source which has a nominal redshift of 5.7. But in the inset, you see that the probability distribution function is rather flat at redshift above 2, which means that for this particular source, we only know that the redshift is likely to be greater than 2. And so this spectral energy distribution and this probability distribution function for the redshift highlights how we can use the PDZs to have a statistically solid approach, even though we don't have spectroscopic redshifts. And the results are pretty intriguing because what we see here are the number counts integrated at redshift greater than 3 on the left and redshift greater than 4 on the right. Our results in red are compared with the predictions of different X-ray luminosity functions, such as the Vito et al., the Wade et al., and the Gili et al., and with the results from the Chandra Cosmos Legacy Survey. And it can clearly be seen that, particularly at redshift greater than 4, there's a significant excess in the number counts in the Chandra J1030 field with respect to the predictions of the different AGN population synthesis models. Here we see 3 different bins of redshift between 3 and 4, between 4 and 5, and between 5 and 6, and clearly the overdensity becomes more and more significant moving towards higher redshifts. So we could be in presence of another overdensity in this field, which is already known to host an overdensity around the J1030 quasar itself at redshift 6.3, and another one around bright FR2 galaxies at a redshift around 1.7. Of course, these results are preliminary because we need a spectroscopic confirmation, as I said earlier on. We very recently got time with LBT mods to follow up some of the redshift greater than 3 population in Chandra J1030. And in particular with the layout that you see here on the left, we will be able to target about 50% of the redshift greater than 3 candidates. 2 of the sources in particular, the one for which you see the SED on the right, have a nominal redshift greater than 5.4, and if confirmed, this will be the farthest, the highest redshift X-ray selected AGN. The observations will take place, hopefully, if the weather is good, at the end of the month, so we hope to have an update with a confirmation or a rejection of the excess observed redshift greater than 3 soon in the spring of this year. So to summarize, in this talk I presented the results of a survey with Chandra of a field centered around SDSS J1030 plus 0524, a 6.3 QSO, which is at the center of a galaxy overdensity. In the past years, the field has been the target of an extensive multi-wavelength campaign. So for the Chandra sources, we have an excellent spectral completeness, about 50% of them have a spectroscopic redshift, and we have a photometric redshift for the whole population. The products, spectra, SEDs, and so on are available for the whole community online, and the first scientific results are already available. In particular, we were able to determine the efficiency of the AGN selected in the X-ray as trackers of large-scale structures, and we were able to compute the number counts for the high redshift greater than 3 population. We found a preliminary evidence of an overdensity at redshift greater than 4, but the results need to be confirmed with a spectroscopic follow-up campaign of the redshift greater than 3 population. And some observations are going to be taken at the end of January, and so more results are soon to come. Thanks a lot for your attention.